can have share screen. Oh, so like just back to Zoom and then screen share. Okay. Perfect. Someone just.
You don't.
Well, let's have this. We don't show all the results. Click on it and everything. Yeah. Okay.
It's not showing.
Sure. Enough.
Still not on the screen. It's the
That's not true. Yeah, in the wrong mode. Just the PDF? Yeah. So if you view here, overview, yeah. And then if I change, yeah, go.
okay, good. Good. Okay. Great. Okay, so now we're going to have Pedro Costa talk to us about some quantum linear system solvers with optimal scaling.
Okay, thanks. So yes, today I'm going to talk about our latest result released. So I did in collaboration with Dominic, which is my supervisor in Macquarie University, also Yuval from UTS, Don Gunn that's here, this now working in the University of Maryland, and also people from Google. This is also the archive number if you want to check the results more carefully. Okay, so why do you care about quantum linear system problem, right? So this is the basis of host new quantum algorithms from machine learning to solutions of partial differential equations. In particular, for differential equations, the idea that if you don't have any analytical solution for your problem, you have to come up with some discretization methods where you're going to end up with the problem, the linear system problem that you want to solve. And then one of the basics problem in math, so AX equals B, we're trying to find the solution for the vector X. So the idea, if you do the quantum calculation, quantum computation of this problem, that you first have to initialize, prepare your state vector state B, where the amplitudes of your vector state B are given as the elements of your vector B. And you are aiming to get the same for the solution after you apply the inverse of the matrix A. And as you know, in HHL, they show how to get this exponential speed up by 3 main steps. So the quantum phase estimation, followed by control rotation, the inverse of the quantum phase estimation. And you might end up by doing some rounds of amplitude amplification in order to increase the probability of success to match the answer at the end. However, this has the downside of this problem that you're not going to get the explicit listing of your solution, right? So you're going to also end up with the proper properties of your vector state X, and then by doing some sampling of that. But given that you are happy with this, so you also have the question about the other parameters that depend on this complexity. So in particular, that I'm going to focus here, the condition number and the absolute allowable error in the solution. So these are just highlighted the results that we got it by using the discrete adiabatic evolution. And so They also, in the HHL, they show the lower bound for in terms of condition, and that should be strictly linear. But you can see that this table summarizes the previous results that anyone could get that so far. And then, but I also can point that after 2018, you have the adiabatic approach being used for the quantum linear system problem that got better and better improvements in these two parameters. So yeah, and then I'm going to move it now for the overview of the presentation that we're going to talk here. So I'm going to start to talk about the adiabatic theorems that the main key to get our results. So the idea of the adiabatic theorems, as you know, we have to have these bounds, how is well we should exchange an energy between your system in order to keep you in the subspace of interest. Very often you are interested about the ground state. So the idea that you want to start with some ground state of Hamiltonian times 0, and then want to end up in the ground state of Hamiltonian times S. And then the idea to get these upper bounds, you have to come up with some ideal evolution. That's the results that are going to show in the continuous version. You have this kind of adiabatic Hamiltonian, and this adiabatic Hamiltonian is associated with the projector operator in the subspace of their interest. And if you see here, this picture, this summarizes this idea that in the subspace of their interest, if you decide to get, for instance, the bounds of this operator, this projector operator, you're gonna see the dependence of the gap between this subspace and the rest of the spectrum. Okay, these previous results here for the continuous case by James and Sarah, they show how to get this upper bound. It's a kind of complicated expression, but essentially what they're doing, they get this upper bounds between this ideal evolution that the adiabatic, in terms of the adiabatic Hamiltonian that they construct, and the actual evolution. And you can see this upper bound, you can be really sensitive of the gap. So they have the polynomial dependency in the inverse of the gap, and also in the first and second derivatives of the Hamiltonian. And then here, if you decide to get a fixed error between these two actual and ideal evolution, you're going to see how long you have to evolve your system in order to get your desired eigenstate. Okay, for the discrete case, actually, it's not too different. So the idea now we have to come up with this adiabatic walk. But now the adiabatic walk is a unitary operator. But it's not clear here yet, but this operator, the adiabatic walk, is also dependent, associated with the projector operator. It's a long expression here, but it's associated with projector operator. But now you have the resolvent here in terms of the unitary, the walk W here. And here the projector is now thinking about it in the complex plane in the unitary circle, in the complex plane. And the idea that here, for instance, if you are interested in the eigenvalues associated with this region in red, here you have the subspace, and the spectrum, the gap here is going to give it by the arc distance between these two regions, right? Okay, so what is the goal for the discrete adiabatic theorem is kind of the same that I showed you previously, the continuous. I want to get upper bounds by the ideal and the actual evolution. So the ideal here I given by this A, which is just a sequence of ideal walk operators, by this kind of this unitary operator here, that a sequence of walk operators that you can rewrite it also these upper bounds in terms of the omega operator, which is just the product between this ideal and actual evolution. And here, for what you are interested to start from a eigenstate of your walk operator at time at 0, and you want to end up in the eigenstate of your walk operator in the time S. Okay, here also have the previous results related with we did it for the discrete version. So, however, in these previous results given by DKS here, you can check in this paper's results here. They only showed that the walk asymptotically operated. So they didn't put any gap dependence of that. So if you want to use this for adiabatic algorithms, you cannot do it because you really need the dependence of the gap. So that's the idea that we decide to cover this topic and decide to fix this issue, and then we concentrate to get this dependence on bound on the gap. So the way that we did is that, so we first replace this ordering scales of the difference of the walk that I showed before. Let's just come back a little bit here. So this ordering scale between the difference of the walk by the strict upper bounds. And the strict upper bounds, we come up with this function CS here. In more general, we did the more higher orders of this difference, more difference between these walk steps. You have this function CKs. And also come up with this idea of multiple step gap. So the multiple step gap, in order to get upper bounds that are needed, you have to consider the difference of walk step in different stands. moments, and you can also depend of in our upper bounds, you depend of until two difference of walk steps. So the idea that when you're moving around this during the evolution between this difference, the gaps going to start to spread around the unitary circle, and you are really conservative in terms that you always take the minimum arc distance between the difference of 2 times walk steps. And then here's just one example, one calculation, how we replace it by these strict bounds and multi-step gap. You can see already the dependence appear in terms of these functions, the dependence of the schedule, and also the gap in this particular one, the gap 1, because I'm taking consider the difference of the difference between the projector operator, which is associated with the walk operator. Then you have to consider the gap 1 other than gap 0, right? Okay, see, after we put all together, we get this expression, this upper bound between our ideal evolution, actual evolution. Actually, what I'm showing here is our less tight version of our upper bound, but it's nicer one because you can really see the comparison with the continuous version. So here I just highlight the difference between how they are comparable in terms of the quantities. So you have also our function C1 and C2 playing the role of the first and the second derivatives in the continuous case. And so you have the same kind of ratios that you can find in the continuous, like you have here the ratios of the first derivative of Hamiltonian with the square of the gap in time 0 and time s. You have the same kind of quantities in terms of functions in a gap. And here you also have the replacement of the integral that you have in the continuous by the sum as respect in the discretization, right? And also the quantities are the same, but you also have extra terms which is not dominant for these upper bounds. Okay, now we're gonna just do a quick comparison. This is really important for our show the improvements that we did in comparison to the continuous. So the idea that if you have some time independent Hamiltonian, so you don't have any other solution, you have to deal with this time order of the exponential, right? They don't have any other solution, and then the problem is the discretization of that. They're gonna come up with some errors. So here you have some previous results that show the optimal way to get this discretization with a really small dependency of the arrow, logarithmic that I'm going to show. It is given by Maria, that's also here, and Dominic Barry. So the idea that if you have to evolve your system from a time 0 to time t, the first thing that you can do here is divide your total evolution in R segments. And the idea is to get these arrows related for each segment and add all together at the end. And the first thing for the discretization here for the time order, you can do by Dyson series. So you have this infinite series, like a Taylor series, and you have to decide where you're going to create the series. And by given order of creation, you're going to have arrow. But you also have to come up with this order of the discretization of the integrals that you're going to have here. So you also have arrows associated with how many elements in the sum you're going to use it for discretizing your integral. And in the end, you're going to you have to add this total accumulation of errors. So the first part here comes from the truncation of the Dyson series, and the other for the discretization of your integral. And then they show these results that if you want to get this error can be bounded by epsilon over R for each segment, because I aim to get the total error in the total epsilon. So they can do that by using this quantity in terms of the truncation that you have to use it in terms of the logarithmic of the R over epsilon. But in our version, we don't need to deal with Dyson series. You have to come up with the cubitization, so the cubitization of the wall. And here you have to construct the blocking coding of the wall. So you have some Hamiltonian, you have to do the blocking code of that, of your Hamiltonian. But how do you do the measurement in the ancilla qubit? You do just have to do the reflection in the end. And you're gonna have this now this unitary of the arc sign of the Hamiltonian. But it's really important that it's really related with this eigenvalues of the original matrix, and of course, it's going to be related with the gaps that you have dependence there. So the way that you measure the complexity of your problem is see how many calls of the oracle for the walk operator needed in order to get your desired eigenstate. Okay, now I'm going to just show the adiabatic approach for the quantum linear system problem. So actually, the one example that I'm going to show is not new. So just going to show the easiest case for A is positive definite emission. So things that Dongan did here with Lin previously. And then the idea here you have two Hamiltonians. So we are aiming to get this final eigenstate for the Hamiltonian H1. So we want to find the eigenpath between these two eigenstates of H naught here and the H1 here. And the idea is you have to do a linear interpolation of this by using a schedule function. And by doing that, you are artificially constructing a time-dependent Hamiltonian. And then by constructing this time-dependent Hamiltonian, you see that you can get the bounds between, you can get the gap between this subspace that are interest or the eigenpath that show in the rest of the spectrum. And here you can see already by having this H1 that you have the matrix already, they're trying to get the solution. You have you're going to see the dependence of the condition number of that in the schedule as well. So that's what you needed in order to solve the linear system problem. How the dependence of how the condition number depends, how the gap depends of the condition number. But another question is how we could find a really good schedule function to solve your problem. So the idea that, as you showed in the previous results, this evolution is really sensitive of the inverse of the gap. So the idea that you want to slow down your evolution while it's close, how the gaps start to get smaller. So the answer you can do it to construct a good schedule function is assuming that you have your schedule that where the derivative is dependent of the power p of your gap. And by doing that, you can get this expression for this particular case. You can get this schedule function that you can already see the dependence of the gap and the schedule and the condition number, and also have the freedom here of these values of 4p in the power. So we also check. So we plug all this together in our theorem that I showed, the last type theorem, and you could see how for this particular value, for instance, how we can get this other one in terms of kappa t here in this big constant factor actually, but this is the dominant part of your upper bound between the actual and ideal evolution. If you want to decide now, okay, I want to fix this error between actual and evolution, you see that the number of steps that are needed for the walk increase linear in kappa. That's what we're aiming for. And here you also test this result, our results. Okay, I also would like to mention that you also have the proofs that it is linear dependent in kappa for all range of p's that we showed previously, that depending on the schedule function. And you also test this numerically using our more tight version of theorem, which is more complicated expression, but you could get 9 times better constant factors over there. So that shows that we have really scope space for improvements of our version of these constant factors here. And just here, just show a plot how we can extract this information about these constant factors by fixing the total number of steps in our theorem and also the condition number. And we are looking for different values of p here, variated different values of p. You're looking for the optimal one here, and you could get estimated how better we could get these constant factors. Now, filter solution also is not a new thing. It also did by Dong and also in Lin previous results. So idea that after you apply a sequence of steps, you want to filter out the undesirable elements, the states that you have there, in order to get the precise epsilon of your solution. And the idea there is to come up with this function f here, going to filter out these undesirable components, and they did it by using the quantum signal processing. But you can have this kind of a drawback in the sense of this a lot of angles you have to optimize in order to find such a function. And you actually isn't up to that. You did it in terms of linear combination of unitaries, can be an easier prescription to get this function. And for this part, you did additional kappa log 2 over epsilon steps of the wall. So in the total, we're going to have it our over complexity of kappa log 1 over epsilon because of these additional steps. And so there's a few comments about lower bound. So actually, there's this Kotori and Arrow have already proven this lower bound, but also they included the dependence of the sparse of the matrix that we didn't include it. And they show that what is really important, they show here that I want to highlight that the combination of these 2 parameters that we did, the kappa and the arrow, which is we got in terms of the optimal, right? So the kappa in 1 over epsilon. But we didn't consider it, of course, in this our approach, we didn't consider the dependence of the sparse, but you know how in general it depends in terms of the blocking coding. So you have the scope also to try to get a better improvements for our version, because typically you're going to depend linearly in the condition A, sorry, the sparse of the matrix A, matrix of your blocking coding. So this is the conclusion. So just a quick review of what I talked today, and also I would like to highlight again that our discrete adiabatic can be given speed ups for all types of adiabatic algorithms, right? So the idea that by removing the Dyson series part, and here that future work that could be interesting to try to get more improvements in constant factors, and also consider the optimizing in terms of the blocking this cubitizer wall in terms of the sparsity. So that's all. Thank you.
Questions can come up to here.
Nice talk. I was wondering, this bounding function you had, CFS, what does that usually depend on?
Are talking about this function?
Yeah, for the discrete.
Oh yeah, that's a pretty good question. Actually, at this moment, it does have independence, right, from the general. But for if you have a specific example to work with, then you're going to see how this function depends on. So for us, for instance, when you did this, you got for this simplest case, you're going to see that dependent on the gap, for instance, or also the schedule function that derived that before. So actually, you don't have it can depend on a lot of stuff, a lot of things. It depends on the problem that you want to work with.
Thanks.
So,
Are there any other questions? If not, let's thank the speaker again.
let's see.